Okay, so we're going to work on solving inequalities, and this inequality again, we know it's a quadratic relationship. It's a polynomial with just two x values. If you were to distribute them, you'd end up with an x squared. So we have a quadratic relationship, which means we have this or this, one of the two, in looking at it. And we're looking for when it's less than 0, and that's referring to our y value. When the y value is at 0, when are we less than that? So in other words, if we're here, we're between. If we're above, it's in this case, technically in here. Okay. So what we're going to do, actually, sorry, it's not in there. It's outside and outside here. This would be above 0. So one way we can do this is in a polynomial, we can always find intervals of our x-intercepts. So what we'll do is kind of rearrange this question to find out when we're equal to 0, okay, which is something we're very common that we're used to doing when, especially when working with quadratics, but essentially any polynomial. Once we're in factored form, we can split up our equation to find out what our x-intercepts are. That makes sense? Okay, so 5x plus 4 is equal to 0, and x minus 4 is equal to 0. We bring everything over, this becomes x is equal to negative 4 over 5, okay, and this is x is equal to positive 4. So in other words, we have our two intercepts, one of them being at 4, and the other one being at negative 5 over 4, okay? Now I can tell you, because I know the a value, or whether this is a positive or negative quadratic, I know that positive, because there's no value here, we assume it's positive 1. Positive quadratics open upwards, okay? So I know when am I below 0? Well, I'm below 0 in between those two values. Right. But I should technically prove it, okay? So if we were to make a number line, the number line really just refers to our x-axis. Okay, so really, you just take your values, don't include the y-axis, and just look at your x-axis. So we're talking about 4 on the x-axis and negative 4 over 5 on the x-axis. And we can test these just to make sure, okay? I have some extra stuff left over from before. So in this case, what we'll do is we'll actually take values before and between and after. So a value to the left of this would be negative 1, a value in between would be 0, and a value after would be 5. So what we can do is we can plug these values into our original equation here to find, it's a silly looking arrow, but to find out what values we get, okay? And essentially we're looking for when they're less than 0, okay? And we've already, using some theory, we've assumed it's when we're between these two values, okay? So let's test this out. We'll do negative 1. We'll plug that in as our first one. Okay, so we had, we'll call the function f at x. So f at negative 1 is equal to 5, oops, that should be negative 1, no longer an x, so negative 1 plus 4, and then negative 1 minus 4. Does that make sense what I've done? I just plugged it in? Okay. So we get negative 5 plus 4, and here we get negative 5. And I can already kind of tell you very quickly, this will be negative 1. Negative times negative 5 gives us what?
5.
Yeah, 5. Well, most importantly, it gives us a positive value.
Right.
It's positive. It is 5, but I want us to focus on that. And because it's positive, positive has to be above our 0. In other words, they're looking at when we're greater than 0. So we know we're positive in this range, okay? And when in factor form, we can probably deduce this really quickly. So our next one, we're going to use the value of 0. So I'm going to write it out, and then we're going to do some mental math to kind of get through this quickly. 5 at 0 plus 4, 0 minus 4. Right away, I'm going to look at bracket to bracket and just focus on whether it's positive or negative, okay? 5 times 0, 0, positive 4, so I know I have a positive in this bracket because it multiplied. And 0 minus 4 is a negative. A positive times a negative is a negative. In other words, we're less than 0. So we know that we're negative. And because of the way quadratics go, it must be positive here, but we'll go through the process again just to make sure. Our f at 5, okay, is equal to 5 times 5 plus 4. Right away, you know that's going to be 25 plus 4. You're going to have a positive value. And then 5 minus 4. Well, that's also going to give us a positive. So I'll kind of jump ahead. That gives us 29, or a positive. And this also gives us a positive, and two positives times each other are a positive. So in other words, it's positive here. So what we have discovered is, and this is how we represent it on our number line, but if we were to write it, we know that our x is greater than 0 when, so you could say, or sorry, our equation, if we called it f at x, so the function is less than 0 when x is less than, what's our number again? Positive 4, but greater than negative 4 over 5. So when we're between those 2 points, it's kind of like writing domain or range instead. We're in between 2 values here. Did that make sense as a number line? So this is kind of like a method of finding x-intercepts and testing intervals. And you can use any number in between those intervals, and it'll always end up above or below. And we can show that. Here's our equation. I think I can actually type in 0. We're looking at when 0 is greater than what we have above. And it gives us our intervals. I can zoom out a little. Okay, and what it's saying is it's between those two numbers. Okay, so we are 0 is, in our case, we're looking at when we're less than 0. Okay, or 0 is greater than our function between negative 0.8, which is negative 4 over 5, and between 4. If we did the opposite inequality, so same thing, but I changed the sign. There you go. It's everywhere else. So outside of those is when we're when our function is greater than 0. Does that make sense graphically? Yeah. Okay, so that's good. And x is greater than negative 4 over 5, or negative 4 over 5 is less than x, and x is less than 4. And we're just going to show that graphically. So our x-intercepts, we're at negative 0.8, which is our negative 4 over 5, like we said, and positive 4. And we'll show that our function is greater than that when we're in between those two values, just like we said at negative 8. Let's zoom in a little so we can see that a little better. Right? So between those two functions, and it would be technically less than outside of that. So we put the 2 up, and everything green would be outside of those functions. Okay.